Hello, welcome to Engineering Mathematics 2. Friends, I hope you are already familiar with Engineering Mathematics 2. One of my friend, Professor Shantarajappa, already discussed about Engineering Mathematics 2, especially differential equation with constant coefficients. Right? So, as you know, the code of the subject is 15MAT21. Friends, myself is Dr. S.S. Benchaldi, working as a professor at Department of Mathematics, Basveshwar Engineering College, Bagalkot. Today, I am going to handle with a linear differential equation with constant coefficients, solutions of second and higher order differential equations, inverse differential operator method, and method of undetermined coefficients, method of variation of parameters. Right. So, I am going to complete all these things within 10 hours. Before that, before starting a linear differential equation with constant coefficients, I can ask some questions on myself. Why I want to study differential equations? Is there any applications in engineering disciplines? Engineering disciplines means maybe electronics and communication engineering, or mechanical engineering, or in electrical engineering. How we are going to use second order differential equation, or how we are going to use higher order differential equation, especially in electrical engineering or in any other branches. Then what are the goals of differential equations, right? And usually what we will do in mathematics classes, solve a differential equation. I will write the differential equation, then I will find out the solution of the differential equation. According to me, that much is not enough to understand about the behavior of a particular differential equation. Now, according to me, we should draw the diagram of each and every differential equation, right? So, that we call it as an usualization, right? So, friends, I am going to usualize all the differential equation or most of the differential equation using a particular software called GeoGebra, right? And how we call it as an GeoGebra? It is the combination of geometry and algebra, right? So, it is possible to draw the solution curve using a GeoGebra. How we are going to draw a curve, you will come to know in this session, right? So, before starting differential equation, right? So, what I feel that I need some preliminaries. Then you may ask, what are the preliminaries, right? Or you may say that we have already studied preliminaries in the earlier classes, right? So, I will ignore that you have not studied differential equations in the earlier classes. It means I am going to begin with a scrap, right? If you don't know anything about differential equation, then such a type of students can also understand what I am going to discuss about differential equations. Right. So, it means differential equations can be written down in various forms, in various forms. It means we can use different notations. What are the different notations, right? So, how it is possible to write down a differential equation, right? Once it is understood, it means different if you are familiar with different notations, then what is the differential equation? So, it means what is the concept of a differential equation. Then I am going to define ordinary differential equation, right? So, we are already familiar with the ordinary differential equation as well as a partial differential equation, right? So, how we are going to define an ordinary differential equation, and what are the objectives of the linear second order homogeneous differential equations, right? And we want to find out a solution of the homogeneous equation. Here we are going to discuss about homogeneous as well as a non-homogeneous equation, right. So, we can discuss one by one how we are going to find out the solution of the homogeneous equation as well as non-homogeneous equations, right. Then how do we say that a particular equation is the solution of the given differential equation? So, it means we want to assume a particular solutions, then we want to verify whether assumed solution is a correct solution or not. Then how we are going to write down a general solution, right. So, if it is possible to find out solution of homogeneous equation and solution of non-homogeneous equation, then what are the characteristics of the solution, right. So, today I am going to discuss all these things, and along with this, if it is possible, I will try to introduce one or two simple initial value problems. And what is the physical meaning of initial value problems? Friends, if you know all these things, then we must know some good textbooks, right. Now, as we have mentioned in our syllabus copy, right. So, you can refer these textbooks. So, one is Higher Engineering Mathematics by B.S. Grewal, or you can refer Advanced Engineering Mathematics by Krejcik. Or along with these textbooks, suppose if you want to acquire how we are going to use a differential equation in various engineering discipline, for that reason we have to refer some other textbooks, namely differential equations by Simmons, right. You can find out lots of applications in this textbook. Suppose if you are interested about medical applications, right. So, medical how we are going to use differential equations in medical field. So, we can find out all those applications in this textbook, right. Along with that, so we can use Advanced Engineering Mathematics by Calais, right. So, you can use these textbooks, not only those two. So, you can refer Engineering Mathematics by Gupta or Engineering Mathematics by one more textbook, Pearson. It is meant for especially for electronics and electrical students, can refer this textbook, Anthony and others. Okay. So, now I want to begin with what do you mean by a differential equation, right, especially differential equation with constant coefficients. Then what are the goals of this lecture, right. So, friends, here we are going to develop for the solution of homogeneous and non-homogeneous second or higher order equations that describes oscillatory phenomena, because equation of this type arise in practical problems involving oscillations in electrical circuits, in the description of many types of mechanical vibration and elsewhere. So, it means here we are going to develop some methods. In the stable oscillatory motions, the particular integral describes the start of an initial value problem, after which it decays, leaving only complementary function that describes the long term behavior known as the steady state solution. So, it means when we consider a non-homogeneous equation, as we know it is containing two parts. So, first part we call it as an complementary function, second part we call it as an particular integral. Here I am going to give a physical meaning of a particular integral as well as a complementary function, right. So, why we need complementary function, why we need particular integral? Suppose if you remove particular integral, what happens, right. So, we will come to know all these things in the one or two sessions. Friends, I told that usualization is very important, especially in differential equations, right. The ability to usualize basic graphs and to interpret them mentally is very important in mathematics courses, not only in differential equations, right. So, one of the powerful and fascinating features of the study of differential equations is the geometric interpretation that we can often place on the solution of a problem. So, it means they have given a differential equation, mathematically we will find out the solution, right. Then we want to draw the graph of the solution equation, right. Then we can interpret it. Okay. Friends, after completing the differential equation, then you may ask what are the learning outcomes, right. So, I wanted to give the learning outcomes before solving the differential equations, because you are already familiar with the differential equation with the constant equations, right. So, upon successful completion of linear differential equation with constant coefficients, it is expected that a student will be able to do the following, right. Now, first one is be familiar with terminology such as constant coefficients. In a given differential equation, what are the constant coefficients? Sometimes we call it as an linear operator. What do you mean by linear operator, right? Auxiliary polynomial. While solving the differential equation, we will use auxiliary equation or auxiliary polynomial. From that, we will find out the roots. From that, we are able to write down complementary function. We are able to write down a particular integral, right. So, for that reason, we should be familiar with all these terms, right. And after the completion of this unit, you must be able to define second order ordinary differential equations, right. So, that is one outcome, or define a linear second order differential equation, right. So, find a general solution to linear second order homogeneous differential equation with constant coefficients when the auxiliary equation has two equal roots. It means, friends, you assume that okay, from the last 1 hour I am able to solve some differential equation. Immediately after that, you can ask what is the outcome of the last hour, right. Then you can say that okay, now I am able to define a second order differential equation, right, and now I am able to find out the solution of second order differential equation. I am able to define a linear operator. I am able to define auxiliary polynomials. So, like that you can ask questions on yourself, then we will learn a new thing, right. So, find the general solution to linear second order homogeneous differential equation with constant coefficients when the auxiliary equation has two distinct roots. Friends, so we know that while calculating the solution from the auxiliary equation, means while calculating the roots from the auxiliary equation, you will get different types of roots, right. Roots may be real and different, roots may be distinct, right. Depending upon the nature of the roots, we are able to write down the general solution, right. Now, exactly in the similar way, find a general solution to linear second order homogeneous differential equation with constant coefficients when the auxiliary equation has two complex roots. If the roots are complex, then solution may be different, right. So, that is an one outcome. Find a general solution to linear second order non homogeneous differential equation with constant coefficients when the auxiliary equation has two equal roots, right. Find a general solution to linear second order non homogeneous differential equation with constant coefficients when the auxiliary equation has two different roots, right. So, it means you must be able to recognize whether the given equation is an homogeneous equation or a given equation is an non homogeneous equation, whether roots are real and equal or roots are different or roots are complex, right. So, depending upon all these parameters, we are able to write down the solution or general solution of the given differential equation, right. So, another outcome, find a general solution to linear second order non homogeneous differential equation with constant coefficients when the auxiliary equation has two complex roots, right. So, find a general solution to a linear higher order homogeneous equation. So far I said that second order, right. So, given equation may be an higher order homogeneous differential equation, right. In that case, how do we write down the general solution? Again, that depends upon whether we will get two equal roots, or you will get different roots, or we will get complex roots. According to that, we are able to write down the solution. So, this is an one outcome of the differential equation, right. So, find a general solution to a linear higher order homogeneous differential equation with constant coefficients when the auxiliary equation has equal, distinct and complex roots. Exactly in the similar way, find a general solution to a linear higher order non-homogeneous differential equation with constant coefficients when the auxiliary equation has equal, distinct, complex roots. Friends, it means that whether the given equation is a non-homogeneous equation or homogeneous equation, order may be 2, order may be 3 or order may be higher one, right. 4th order, 10th order differential equation, right. How do we find out the solution? Is it clear, right. So, again that depends upon the auxiliary polynomial. We want to find out the roots. Depending upon the nature of roots, we are able to write down the solution, right. So, you will come to know all these things. Along with those outcomes, right. So, use the method of undetermined coefficients to find the general solution of second order differential equation, right. So, it means you want to familiar with the undetermined coefficients. It is a particular method to solve a differential equation, right. So, use the method of variation of parameters to find the general solution of second order differential equation, right. I am going to introduce one more method, namely variation of parameters, right. Sketch the graph of a solution of a differential equation. It means after solving each differential equation, we must be able to draw the graph of the solution of a differential equation. Then you can interpret, right. So, interpret the results and compare with the physical intuition. Define second order initial value problem. Okay. So, once we are able to define a second order linear differential equation, along with that you must be able to define second order initial value problem. Then you must ask, what do you mean by initial value problem? I am going to explain about the initial value problem, right. So, define higher order initial value problem. These two are also an outcome, right. Interpret the initial conditions, right. So, it means along with each differential equation they will give some conditions, right. What is the physical meaning of those conditions, right. So, I am going to explain, and we can treat it as an one outcome of the differential equation, right. A function may be determined by a differential equation together with initial conditions. It is also an outcome, right. Okay, friends, so far we have seen what are the outcomes of the differential equation, right. So, now if I want to define a differential equation, as I have mentioned earlier, we need some preliminaries. Then you may ask, what are the preliminaries we need to define a differential equation, right. First one is a notation, because differential equations can be written down in various forms, right. Now, first one is Leibniz notation. Differential equations can be written down using the symbol dy by dx, or d square y upon dx square, or d cube y upon dx cube, and so on, d raised to n y upon dx raised to n, right. So, friends, I hope you know these symbols. We have already used these symbols in differentiation. So, you know that the meaning of dy by dx is derivative of y with respect to x, right, and it is containing two variables, namely x and y, right. So, y is an dependent variable, x is an independent variable. Exactly in the similar way, so this is a second derivative. It means you can differentiate y with respect to x how many times? 2 times, right. Suppose if the symbol is like this, what it represents? You want to differentiate the function y how many times? 3 times, right. Suppose if I replace 3 by 4, it is understood that y is a function or given function, it can be differentiated 4 times, and in general we know that because we are already familiar with nth derivative, right. So, I want to differentiate the given function how many times? N times, right. So, you will get d raised to n y upon dx raised to n, or what we call it as an nth derivative of the given function, right. So, this is one notation can be used while defining or while writing a differential equation, right. Now, exactly in the similar way we can use few more notations to write a differential equation, right. So, one more notation is prime notation. Sometimes instead of writing dy by dx, we will use the symbol y single prime, right. I repeat once again, y single prime, it represents dy by dx, right, or y double prime, y triple prime, and so on, right. So, either you can use dy by dx or we can use these notations, right, or we can use Newton's dot notation, right. So, for example, if I want to write d square s upon dt square is equal to minus 32, right, it is an equation. Now, I want to use this equation, I want to rewrite this equation using Newton's dot notation. How I am going to write? It is very simple, s to the power c double dot, right, is equal to minus 32. Is it clear? So, this equation can be written down in this form. S double dot means it indicates that d square s upon dt square, or an equation like this, ds by dt is equal to minus 32, you can denote s single dot is equal to minus 32. Single dot means it represents ds by dt, as clear, right. Or an equation like this, d square x upon dt square plus 2 lambda into dx by dt plus omega square x is equal to f of t, as clear. Sometimes we will write a differential equation using these symbols, or sometimes we will write a naught d square y upon dt square plus a1 dy by dt plus a2y is equal to f of t, or sometimes we will use notations like this, capital I into d square theta upon dt square plus k into d theta upon dt plus mu into theta is equal to f of t. Now, you observe these equations, we will come to know that in some equations I have used theta, in some equations I have used x, right, or y, right, independent variable is also x, right, or t. Is it clear? So, like that we can use different notations to represent a differential equation, or you can write down an equation like this, c into x single dot plus kx is equal to f of t. Is it clear? Or you can write down I into theta, Newton's dot notation, double dot plus k into theta is equal to f of t, or sometimes we can use this notation m into x double dot t plus k into single dot t is equal to 0. Friends, so from this slide we will come to know that we can use various notations to represent a differential equation, right. So, that is why I told that you can use different textbooks. You may ask why we want to use different textbooks. So, we will come to know various forms of a differential equation. It means a same differential equation can be represented in various forms using different symbols that we will come to know when we are going to refer more than one textbook, right. So, friends, along with this symbol, so we need another notation called differential operator, right. So, in calculus, differentiation is often denoted by the capital letter D. D by dx is equal to capital D into y. The symbol capital D is called the differential operator because it transforms a differentiable function into another function, right. say for example dy by dx is equal to capital D into y, right. It means sorry, dy by dx can be written as a capital D into y, or d by dx of dy by dx can be written as d square y upon dx square, that is equal to capital D into dy, that is equal to d square y, or d by dx of d square y upon dx square can be written as d cube y upon dx cube, or the same thing can be written as capital D into d square y, that is equal to d cube y, or in general d raised to n y upon dx raised to n, that is equal to d raised to n y. Now, here d is called a differential, capital D is called a differential operator. Okay. Now, I have given some preliminaries about a differential equation, right. So, we must be able to define a differential equation, or you can ask one question on ourselves, what is a differential equation, or what is the concept of a differential equation. Friends, solution is also very simple. A differential equation is an equation relating some function f to one or more of its derivatives, right. It means differential equation is also an equation. Friends, we are already familiar with equation. Say for example, x plus y is equal to 0, right. It is also an equation. Then you may ask, can we call it as an differential equation? Answer is very simple, no. Then you may ask, why can't we call it as an differential equation, right. Answer is also very simple or straightforward, right. So, because that equation does not containing any derivatives or differential coefficients, that is why it is not an differential equation, right. Here I have written one example, d square f upon dx square, right, plus df upon dx, right, plus f square is equal to sin x, right. This is an example of a differential equation. Instead of y, here I have written another notation, namely f. Here f is a function of x, is it clear? Or you can replace f of x by y, or you can replace any other notation, right. So, this is an example of a differential equation, right. So, when we want to call it as a differential equation, then we must identify whether that equation containing derivatives or differential coefficients. If it is containing derivatives or differential coefficients, then we can say that it is a differential equation. That is why here I have written, note that this equation involves a function f together with its first and second derivative. It is containing f and its first derivative as well as a second derivative. For an equation to be a differential equation, at least some derivatives of f must appear. Just now I have mentioned. Okay. Now, we are able to define a differential equation, or I can say that now we are able to identify whether the given equation is an differential equation or not, right. Along with that, we must know what is the order of the differential equation, because it is an very important, right. Whether the given equation is an first order differential equation or second order differential equation or higher order differential equation. Then you may ask, how do we come to know that what is the order of the given differential equation, right. Or you can verify whether given equation is an ordinary differential equation or partial differential equation. Is it clear, right. So, I can say that given equation is an ordinary differential equation, or short form what we use ODE, right. So, not involve partial derivatives, that is it involves a function of a single variable, right, and the ordinary derivatives of that function. Just now I have shown one example, right. That example containing only ordinary derivatives dy by dx, d square y upon dx square. So, it means it is understood that y is a function of a single variable, or f is a function of a single variable. Along with such type of functions, any equation containing ordinary derivatives, such type of equations we call it as an ordinary differential equations, right. Otherwise it is called partial differential equation, right. Usually we write short form PDE, right. So involves partial derivatives. Any equation containing function, right. Function means that function may be a variable of more than one variable, right, and along with the partial derivatives. Such a type of equations we call it as an partial differential equations, right. So friends, here I am not going to discuss about partial differential equation, right. Okay, just now we talk about what is the order of the differential equation, right. Order of the differential equation is the order of the highest derivative present in the differential equation. So for example, you assume that they have given one differential equation, right. Say d square y upon dx square plus dy by dx is equal to 3x into sin y. Now I want to identify the what is the highest derivative present in this equation, right. So two derivatives are present in this equation, dy by dx, d square y upon dx square. I have to identify highest derivative. What is the highest derivative? D square y upon dx square. Therefore, the order of this differential equation is 2, right. Suppose the same equation containing one more term, namely d cube y upon dx cube. In that case, if I ask what is the order of that equation, you can say that third order differential equation. Suppose the same equation containing one more term, namely d raised to 4 y upon dx raised to 4, then order of this equation becomes 4. Suppose the same equation containing a term like d raised to n y upon dx raised to n, in that case this equation means the order of this equation becomes nth order. It is very simple. You want to identify highest derivative present in the equation, that becomes the order of the differential equation, right. So that is why here I have written second order ordinary differential equation. Is it clear? And exactly in the similar way, you are also familiar with what is the degree of the differential equation. It is very simple. Say for example, here they are given this equation. We know that this is an second order differential equation. I have identified highest derivative present in the equation, that is d square y upon dx square. Now I want to obtain what is the degree of this term, right. The degree of this term is 1. Then I can say that so this is a second order first degree differential equation. It means while observing degree, you want to identify highest derivative present in the equation, and you want to identify what is the degree of that term, that becomes the degree of the differential equation. So it means so this is a first degree second order differential equation, right. Now exactly in the similar way we can define PDE, means partial differential equation, right. It is containing some partial derivatives as well as some other variables. This equation is called first order partial differential equation. Okay, so now we are able to understand what you mean by ordinary differential equation, right. We are able to define order and degree of the given differential equation, right. So now why can't we think about a linear second order homogeneous differential equation? So for example, they have given a linear second order homogeneous differential equation. How do we find out the solution of such type of a differential equation, right. So what are the objectives? Define a second order ordinary differential equation, define a linear second order differential equation, find a general solution to a linear second order homogeneous differential equation when the auxiliary equation has two equal real roots, distinct roots, complex roots. So now we shall think about all this. Okay, friends, now we want to define a differential equation. So far I have not defined a differential equation. I have given what do you mean by a differential equation, or what is the concept of a differential equation. Actually, how we are going to define a differential equation, especially a second order differential equation. A second order ordinary differential equation has the form d square y upon dx square is equal to a function of x y dy by dx, right. Suppose if I want to define a second order differential equation, that equation or such a type of differential equation must contain the symbols d square y upon dx square and function of x y dy by dx, right. If the second order differential equation can also be written as, right, as I have mentioned in the earlier slides, right. So, differential equations can be written down in various forms. So, one form is a into y double prime plus b into y single prime plus c into y is equal to x. The differential equation is a linear second order differential equation, right. If it does not fit this form, it is a non-linear. Any equation is not equal to this form, then we can say that such type of equations are called non-linear differential equation, right. So, friends, you observe a right hand side, it is containing capital X. Suppose if it is 0, sometimes it may be equal to 0, that is why I can say that suppose if I put capital X is equal to 0, then linear second order differential equation is homogeneous, right. Suppose if the right hand side member is 0, then I will call this equation or such a type of equations as homogeneous equation, right. So, you may ask, suppose if it is not equal to 0, then what happen? If x is not equal to 0, it is a non-homogeneous equation. Is it clear, right? You remember, sometimes a right hand side may be equal to 0, a right hand side may not be equal to 0. Suppose equal to 0, we call it as an homogeneous differential equation. If it is not equal to 0, non-homogeneous equation, right. So, you assume that they have given a homogeneous equation, then how do we find out the solution of such a type of equations, right. Solutions to homogeneous linear second order differential equation using the auxiliary equation. Say for example, the given second order differential equation can be written in this form. It is a symbolic form, right. As I have mentioned, our equation containing dy by dx, and I have replaced d by dx by capital D. Then I will put m is equal to capital D. Then you will get this equation a into m square plus b into m plus c is equal to 0, right. So, clearly it is an auxiliary equation, right. From this you can find out the solution. How do we find out the solution, right. So, it is an algebraic equation, right. It is an algebraic equation. So, I hope you will get 2 roots, right. So, if m1 and m2 are 2 distinct real roots, right. So, friends, you know the formula, we can find out it is a second degree polynomial, or what we can say that it is a quadratic equation. You know the formula, I can find out m is equal to minus times of b plus or minus b square minus 4ac divided by 2a. We are already familiar with that formula. Using that formula, so we can find out, right. So, you observe, so within the bracket here I have written b square minus 4ac is greater than 0. Why I have written b square minus 4ac is greater than 0? It is very important, right. What I have written, if m1 and m2 are 2 distinct real roots, it means if b square minus 4ac is greater than 0, then you will get m1 and m2. It means you will get 2 distinct and real roots. Is it clear, right? Then in that case, what is the solution of the given differential equation? Given solution of the given differential equation can be written y of x. It means y is a function of x is equal to c1 into e to the power m1x plus c2 into e to the power m2x, right. I will explain how do we say that solution can be written in this form only if 2 roots are real and distinct, right. Okay. If m1 is equal to m2, that can be called as m, because when 2 roots are same, some say it is some constant, say m, or real and equal roots. When we get real and equal roots, that is also important, right. So, friends, we will calculate b square minus 4ac, right. Suppose if it is equal to 0, then you will get 2 equal roots. In that case, how do we write down the solution? That is also important, right. So, y of x is equal to c1 into e to the power m into x plus c2 into x into e to the power m into x, right. I will explain why we want to write the solution in this form only when two roots are real and equal, right. So, exactly the similar way, if m1 and m2 are two complex roots, right. So, friends, we know that if the roots are complex, we are able to write down in this form alpha plus or minus I beta, right. So, when we get complex roots, b square minus 4ac is greater than 0, right. So, then you will get two complex roots. If the roots are complex, then what is the second order homogeneous equation? Solution can be written in this form, y of x is equal to c1 into e to the power alpha x. Where is the alpha? Alpha is the real part, right. Into the bracket, you can write on cos of beta x plus c2 into sin of beta x, or if you do not want to take out e to the power alpha x, you can multiply term by term, what I have written here, c1 into e to the power alpha into x cos beta x plus c2 into e to the power alpha x sin beta x, right, or you can take out e to the power alpha x outside. Okay. So, friends, depending upon the nature of the roots, we are able to write down the solution of the second order differential equation, right. Then you may ask, what do you mean by a solution, or what are the characteristics of a solution, right. Solving an equation, here I have written an second order differential equation, right, is to find the function. Solving means what? After solving, what we will get? So, it is containing an unknown function. What is the unknown function? F is the unknown function. I will get the value of f. That is why here I have written is to find the function f. So, it means that suppose if we are going to solve a differential equation, means we are going to find out the solution of the function, solution of the unknown function, right. So, because each and every differential equation containing an unknown function, right, namely in this case f is the unknown function, right. So, if you are going to solve this equation, means it is understood that you are going to calculate what is the value of f, right. Note that unknown function denoted by y, as I have mentioned, instead of f you can write down y, or you can write down y of x, right, or you can write down f of x like this, right. So, we can use different annotations, is it clear? That is why I can recall one statement, a fundamental new paradigm, right. When we solve an algebraic equation, we seek a number or perhaps a collection of numbers. It means that when we are able to solve an algebraic equation, so we will get a number or more than one number. When we solve a differential equation, we seek one or more functions, right. So, that we will come to know, or that is the characteristics of the solutions. Okay. For example, you can consider a differential equation y double prime minus y single prime plus 6y is equal to 0, right. Immediately you can ask one question on yourself, what is the order of this equation, right. So, you can say that it is a second order differential equation. How do we say that it is an second order differential equation? Because it is containing derivatives, because it is containing highest derivative. What is the highest derivative? 2. That is why you can say that it is an second order differential equation. Is it clear? And immediately you can ask, what is the degree of this differential equation? It is an first degree differential equation, because degree of the highest order derivative is 1. That is why we can say that this is the first degree second order differential equation, right. And we are also familiar with homogeneous and non-homogeneous equation, whether is it an homogeneous equation or not. So, clearly it is an homogeneous equation. How do you say that it is an homogeneous equation? Because right hand side term is 0, that is why I can say that it is a homogeneous equation. Is it clear? So, if it is an homogeneous equation, how do you find out the solution, right? I am not going to find out the solution of this equation, because I am going to verify here, I am going to assume two functions, namely e to the power 2x and e to the power 3x. I may call it as an y1 and y2. Here y1 and y2 are functions of x, right. So, now I can assume these two as the solution of this equation. I do not know whether it is correct or wrong, right, but I have to verify, right, whether these two are the solution of the given differential equation or not, right. So, if I want to verify, you may ask what we want to do. It is very simple, right. So, we have assumed y1 is equal to e to the power 2x is one solution of this equation, right. What I will do, I will replace y by this solution. Is it clear, right. And similarly, I want to find out y single prime. Y single prime means what? I want to find out the derivative of y. Is it clear? Here y is equal to e to the power 2x. I will differentiate this function. Is it clear? Derivative of this function is what? Right. So, it is of the type e to the power x, a into e to the power x. So, it means I hope you will get 2 into e to the power 2x. Is it clear? Right. And given differential equation is also containing y double prime, right. I have to differentiate this function how many times? 2 times. So, what I will get? 2 into e to the power 2x. Is it clear? Right. Okay. I will substitute in the given equation. That is why here I have write down, right, y1 double prime minus 5 times of y1 single prime plus 6 y1 is equal to the value of y1 double prime 5 times of y single prime plus 6 into y, right, and simplify. E to the power 2x is common from all these terms. You can take out 2 into 2 is 4, right, 5 into 2 is 10, right, 6. Simplify 4 minus 10 plus 6 is equal to 0. Is it clear? So, it means first solution or what we have assumed e to the power 2x will satisfy this equation. It means when I replace y and y prime, y double prime, it becomes 0. Left hand side is equal to 0 or right hand side is equal to 0. Then I can say that it is satisfied. Exactly in the similar way, right. And we have assumed one more solution e to the power 3x and I have called it as y3x, right. And I want to replace y by this function. Is it clear? Similarly, I want to differentiate. Is it clear? Derivative of e to the power 3x is 3 into e to the power 3x and I want to differentiate one more time. It means I want to find out second derivative. Is it clear? Right. So, I hope you will get 3 into 3 e to the power 3x, right. So, again observe all these terms containing e to the power 3x. 3 into 3 is 9, 5 into 3 is 15, right, 6. Is it clear? Along with the signs I have written here, right. Simplify. So, 9 minus 15 plus 6 into e to the power 3x. Again after simplification you will get 0. Friends, we will come to know that these two functions satisfy this differential equation, right. This process of verifying that a function is a solution of the given differential equation is entirely new for us. Is it clear? Right. Okay. Anyhow, we have verified both the functions satisfied the given differential equation. Similarly, it is easy to verify or it is easy to check that any function of the form y of x is equal to c1 e to the power 2x plus c2 e to the power 3x, right, where c1 and c2 are arbitrary constants is also a solution of the differential equation. Is it clear? Friends, what we have observed, they have given a second order differential equation and we have assumed two different solutions, right. Then we have verified whether both the solutions satisfies the given differential equation or not, okay, and both the differential equations satisfied the given differential equation. Exactly in the similar way, you can combine both the solutions. Is it clear, right? What I have written here, e to the power 2x, e to the power 3x, along with the two arbitrary constants. You can verify, right, whether this equation satisfies that equation or not. It is very simple. That equation containing y, replace y by this function, and I want to differentiate this function. I will get y1x and y2x. I will substitute and I can verify, right, and this function will also satisfies the given differential equation, right, along with the arbitrary constants. So, this principle we can call it as an superposition principle. That is why I have defined superposition principle for homogeneous equations. Let y1 and y2 be solutions of the homogeneous second order differential equation. What I have written here, y double prime minus 5 times of y single prime plus 6y is equal to 0 on the interval I. Then the linear combination y is equal to c1 y1 plus c2 y2, right, where c1 c2 are arbitrary constants is also a solution of the interval. Just now I have explained that concept or that process, we call it as an superposition principle, right. So, by using this principle only, we are able to write down the solution of the second order differential equation or a solution of the higher order differential equation. Friends, here we can observe one more important notation important observation, right. So, when we are going through the procedure to solve a differential equation, right, how do we know that when we are finished, right. So, in the process we will come to know that whether I am able to obtain final step or not, or how do we say that when we will come to know whether I am able to obtain the final step or not. The answer is that the solution process is complete when all derivatives have been eliminated from the equation. For then we will have y expressed in terms of x, at least implicitly, right. So, it means given differential equation may contain some derivatives, we have to eliminate all those derivatives. We shall find a number of independent solutions equal to the order of the differential equation. Then we shall be able to form a so called general solution by combining them as in the form of y is equal to c1 e to the power 2x plus c2 e to the power 3x, where c1 c2 are arbitrary constants. Friends, so far we have considered second order differential equation. First we have assumed e to the power 2x and e to the power 3x are the two solutions of the equations, right. Then I said that you can verify this form of equation will also satisfies the given equation, right, that can be verified easily. Now I will call it as an general solution of the given equation. How do you say that it is the general solution of the given differential equation? Because given differential equation is an second order differential equation, and this equation containing two independent solutions, namely these two functions, and we have combined these two solutions, we have formed a new equation, right. So, we know that this equation will also satisfied that equation, and we may call it as an solution, general solution of the given differential equation. Friends, in the next session we are going to discuss about what do you mean by an initial problem. Thank you.